in this episode, we will be trying to evaluate the entropy of a classical ensemble system based on partition function. In the last episode, we have derived the expression for the canonical distribution as PR is equal to e raised to minus beta ER divided by sum over R e raised to minus beta ER. So, this is what we define as the canonical distribution, and we know that beta is equal to 1 by kBT. And then we also discussed that, or we defined a quantity known as the partition function, because this can be written as 1 by q exponential minus beta ER, right, and where the partition function q was defined to be equal to sum over R exponential minus beta ER. So, q is equal to sum over R exponential minus beta ER. This is how we define the partition function. So, another question is that what is the role of partition function? Very simply saying, the energy of their ensemble is distributed among various microstates based on partition function. So, basically partition function defines or tells us how the energy of an ensemble, here we are talking about the canonical ensemble. So, the energy of the canonical ensemble is distributed among different microstates, right. So, that is the first and foremost explanation for a partition function. So, therefore, you can see that fundamentally the partition function describes the statistical property of a system in thermal equilibrium, right. So, here so it defines distribution of energy. Additionally, it defines the statistical property many times it is told that the partition function is actually the fingerprint of a statistical mechanical system, especially when we are dealing it in the classical regime. So, we can also tell that the partition function describes how an ensemble is partitioned among various microstates. And then another important term is what we call as the sum of states. So, at least in some textbooks you will see the partition function being otherwise defined as something called the sum of states, because basically the partition function connects the weighted number of states a system can occupy, right. So, you have the total microstates and the energy is distributed among various microstates, and the partition function will tell us how much each of these microstates are having weight in terms of the energy. So, these are the three important significance or the characteristics which we can study based on the partition function. So, in statistical mechanics, especially in classical statistical mechanics, whenever we have we are having a real system, first of all our attempt should be to evaluate its partition function. So, it is a skill for any system, any given system given to you, you should be able to evaluate its partition function. We will be definitely doing couple of examples in the coming episodes. Now, our attempt in this episode is mainly to talk about the entropy of a canonical ensemble system. For the purpose, let us Let us consider an ensemble. So, here we know that ensemble is having, every ensemble is made up of different elements. So, if you remember in the episode on ensembles, we defined the ensemble as system of elements, right. So, therefore, in this system, say we have script n number of elements. So, imagine that you have script n number of elements in our system. So, that means that you are going to number your system as say 1, 2, 3 up to script n. These are the identification numbers of these elements 1, 2, 3 up to script n you can define. And the total energy we call as epsilon or capital E, whatever it is. So, epsilon be the total energy of the system. Right. And if that is the case, then we should have some kind of an eigenvalue which will define or the energy eigenvalues of the elements. Let us define it by ER, right. ER is equal to where R is equal to 0, 1, 2, 3 etc. So, therefore, based on these informations, now I can write that sum over NR is equal to script n, right. Sum over R, NR is equal to script n, and sum over R NR ER is equal to script n U, where U is my average energy per element. This is obviously equal to E, right. So, yeah, so I should be writing like that. So, sum over NR is equal to script n and sum over NR ER is equal to the total energy E, which I can write in terms of the script n as script n U. I should be rather writing like this, where U is the average energy per element of the system. Therefore, based on this expression, I can definitely write this as equal to sum over NR ER divided by script n can be written as sum over PR ER. Why? Because sum over NR divided by the script n, it can be calculated as, can be told as PR ER, and obviously since I am having the summation here, I should be mentioning that also. Is equal to summation over R PR ER, right. So, this is how we can define this system. Now, the canonical the distribution function PR is equal to e raised to minus beta ER by sum over R e raised to minus beta ER, right. This was our canonical distribution function, which we can substitute over here for the function PR, and then if I substitute that, I can get the expression for the average energy U as equal to average energy U is equal to sum over R ER exponential minus beta ER divided by sum over R exponential minus beta ER. Now, if we look into this expression, my mathematical experience will tell me that I can obviously express this function as a differential. A differential of what? If I take a differential in terms of beta. So, this can be written as minus dou by dou beta of ln sum over r exponential minus beta ER, right. I can write this u is equal to minus dou by dou beta of ln of sum over r exponential minus beta ER. So, this is a very useful expression for us, and in our derivation towards the expression for entropy, we know that the Helmholtz free energy A can be written in terms of the u as A is equal to u minus Ts, right. So, this is a very famous expression, which means that I can write it as u is equal to A plus Ts, and the entropy S can be expressed in terms of A, which we have done in our thermodynamics classes probably. S is equal to minus dou A by dou T. So, we will use both this expression S is equal to minus dou A by dou T and u is equal to A plus Ts into this expression, which means that I can write u is equal to A minus T into dou A by, I just simply substituted this over there, right, which means that which I can write this differential can be simplified or can be rewritten as equal to T squared into dou by dou T of, right, A by T. So, T squared into dou by dou T of A by T. Again that the T squared into dou by dou T of A by T can be written as equal to dou of A by T divided by dou of 1 by T, right. So, that is how. Now, we have two expressions for u now. U is equal to this one. So, as the first expression, and now for u again, now we have the new expression which is this one. So, we will equate the equation number 1 and the equation number 2. So, or comparing to these equations, I can write now dou of A by T by dou of 1 by T is equal to minus dou by dou beta of ln sum over r exponential minus beta ER, right. Equation number 1 was this one and the equation number 2 is this one. So, we just equated both those equations, and then I can rewrite this as, I just divide it by k in the left hand side in the denominator and in the numerator. So, therefore, I can write this as equal to dou of A by kt divided by dou of 1 by kt is equal to minus dou by dou beta ln sum over r exponential minus beta ER, right. This was the expression. So, therefore, I know that beta is equal to 1 by kt. This is a known information to me. Beta is equal to 1 by kt. So, I can express now this the denominator over here as in terms of the beta, So, this will be dou of A by kt by dou of beta is equal to minus dou by dou beta of ln dou by exponential sum over r exponential minus beta er, and I cancel the beta part over there and I differentiate there, then I can write this as equal to A by kt is equal to A by kt is equal to minus ln exponential minus beta er, right, sum over r exponential minus beta er. A by kt is equal to minus ln sum ln of minus ln sum over r exponential minus beta er, or otherwise A is equal to kt ln sum over r exponential minus beta er, right. This is what ln sum over r exponential minus beta er, we know this already. What is it defined? We know that it is our partition function Qn. So, therefore, I can write this as equal to minus kt ln q. So, A is equal to minus kt ln q, which means that now we know that A is an extensive parameter, right. By definition, A is an extensive parameter. We have defined what is an extensive and intrinsic parameter in our classes on the Gibbs paradox, and I am not trying to do it again here. So, A is an extensive parameter, which means that since this expression is holding, this equation is giving me a new information that Q is also an extensive parameter. Which is a very useful quantity or the useful information for me. And from the discussion we know that we have defined the probability as equal to PR is equal to what? PR is equal to 1 by q exponential minus beta er. So, this we know, right. So, take logarithms on both the sides. Take logarithm on both sides, then I can write ln PR is equal to ln of 1 by q, which I can write it as minus ln q, ln of exponential minus beta er, which means it is ln and the exponential will cancel out, and therefore, I can write it as minus beta er, right. So, ln PR is equal to minus ln q minus beta er, and if I take the average on both sides, average ln PR is equal to minus ln q minus beta average of ER, right. In this expression, my average of ER means that I can express it in terms of again the U and the PR. Average ER is equal to U divided by PR. So, let me substitute that over here, or let me utilize that information over here. I can write average of ln PR is equal to minus ln q minus beta u by summation over PR, and if I take the PR over to this side, PR into average of ln PR does not have any significance. The average or without the average, it is the same thing. So, I can simply write PR ln PR is equal to the minus summation over R PR ln Q minus beta U, right. Summation over R PR is equal to 1. So, therefore, I can write the PR ln PR is equal to, here there is a summation. So, summation over R PR ln PR is equal to, this is 1, therefore, ln Q minus beta U, and which I know that is equal to minus ln Q. We know that it is equal to A by KT, right. KT ln Q is what we defined it as the A function. Here we have written A is equal to minus KT ln Q, which means that minus ln Q is equal to A by KT. So, substituting that over here, I can write A by KT minus beta U, U by KT, because beta is equal to 1 by KT, right. So, based on which I can write beta into A minus U, and A minus U is equal to A is equal to U plus Ts. So, therefore, I can write this as beta Ts, right, minus beta Ts, right. So, sum over R PR ln PR is equal to minus beta Ts, or I can write this as equal to minus over R, sum over R PR ln PR is equal to minus beta Ts, and beta is equal to 1 by KT. So, is equal to, therefore, this is equal to minus S by K, or S is equal to minus K sum over R PR ln PR, right. So, this is what the entropy of a canonical ensemble system looks like. We have already defined the PR, right. PR is equal to e raised to minus beta ER by sum over R exponential minus beta ER, and there we have the Q also. So, if we know the Q, we can calculate the entropy of the system. And another significance is that if we know that at temperature at T is equal to 0, how the system will behave? At T is equal to 0, I know that my S should be equal to 0. So, which means that if the left hand side S should be equal to 0, which means that my ln PR should be equal to 0. At what condition my ln of any quantity will be 0? Which means that the variable has to be what? 1. So, ln of 1, which is equal to 0. That means at temperature 0, PR is equal to 1. That means at temperature at 0 Kelvin, there is only 1 microstate which are possible in the state that defines a system which is in the ground state. So, our equation which we evaluated for the entropy correctly predicts how the system will behave at 0 Kelvin. So, similarly you can extend the argument for what will happen if PR is getting bigger. So, you can think it yourself and try to get into more problems which are dealing with the real world examples of evaluation of the entropy of the system. So, we have seen how do we define the partition function of a canonical ensemble, and also how do we calculate the or evaluate the entropy of a canonical ensemble based on the partition function. Now, our task should be to take up real world examples which are more connected with the real world systems. So, which we will be trying to do in the coming episodes. Thank you.